तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we shall continue our discussion on looking at the conditions for proper operation of the I squared L cell, that is how to ensure that the transistor, the NPN transistor in an I squared L cell actually goes to saturation, okay, because as we had seen, the condition of the PNP transistor at the base, okay, that is the current source, this transistor, okay, this PNP transistors is actually in saturation, okay, and so it has to be ensured that the base of this transistor, NPN transistor, gets sufficient current, okay, in order to drive this transistor to saturation. All right. So we had started that discussion, and so this is the I squared L cell, and this is a transistor with, say, n collectors, okay, n is any number, okay, and as we had said that we will assume that this multi collector transistor of n collector, having n collectors, is actually n transistors in parallel, that is, okay, the base and emitter are in parallel, okay, the bases are all shorted, emitters are all grounded, okay, and they just have separate collectors. So basically they are n transistors, okay. So and the transistor parameters which we will talk of, like IS, the Nebers-Moll model, okay, refers to each individual transistor, okay. Okay, IS, when we say, is actually the saturation current for one of these transistors, okay. All right. So again, the model which we will be using is the Ebers-Moll model, okay. I will just draw it once more, okay. So you have three current sources, okay, and this is the collector, this is the base, this is the emitter. So this current source is IS by beta R exponential VBC by VT minus 1. This one is IS by beta F exponential VBE by VT minus 1, and this is IS exponential VBE by VT minus exponential VBC by VT, okay. So using this model we will try to derive a condition for the values of these parameters of the individual transistors, that is IS, okay, and beta, okay, of the NPN and PNP, which must be satisfied so that this cell works, okay, that is this transistor, NPN transistor, goes to saturation, okay. Now the condition for saturation we know is that when the base current, the beta times IB is greater than IC, all right, okay. So if you consider them as n transistors, okay, so the total collector current for the n transistors is n I naught, the total base current is going to be, so this is beta, I write n here, okay, to differentiate between the beta of the forward and the reverse, okay, all right, beta n ISN, so base current of the NPN transistor, if you go back again to this model, okay, the base current is given by the sum of these two current sources. Okay. Now, assuming that VBC is less than VB, although the transistor goes actually is in saturation, but when it is just going into saturation, okay, VBE is much greater than VBC, may not be very much greater, but because of the exponential relation. Okay. If this is 0.7 and this is VBE is 0.7, VBE is 0.5, okay, 0.7 by VT exponential is going to be much greater than 0.5 by VT exponential. Okay, because of the exponential nature, all right. So, we can neglect this part, okay, and we can just take, so, all right, exponential VB by VT. Here what I will do is, again I just write this voltage here, I call this voltage V2, okay, and I call this voltage at this point V1, okay, all right. Of course, this is coming from some external resistance, okay, but this voltage is V1, okay, and this voltage here as V2, okay. So, this becomes exponential V2 by VT, okay. So, this is for one transistor, all right, and this must be greater than I naught, where I naught is the current, okay, flowing in here, okay, all right. Now, here I call this I naught, okay. So, the condition for saturation is ISN exponential V2 by VT must be greater than I naught. So, this condition must be satisfied. Okay, all right. So, of course, if you have n transistors, the total collector current is going to be n times this, and here you have to consider n times the total base current is n times. So, it's given by this expression. Okay. Now, what is I naught? I naught is the current for this PNP transistor. Okay. Now, for the PNP transistor, the base, you see that the base emitter voltage is going to be around 0.7 volts of that order, okay, whereas the base collector voltage, this is this transistor is going to is in saturation. We are looking at the condition for saturation, okay. So, the base collector voltage is around 0.2 volts, okay. So, the base collector voltage is much less than the base emitter voltage, okay. So, when we look at the PNP transistor, okay, so it is in the active region, this PNP transistor, okay, I call this P2 and let me call this P1, okay. So, P2 is in active region, all right, and so here we can say VBC for the P2 transistor is much less than VBE, all right, the base collector voltage is much less than VBE. So, the collector current can be expressed as I naught, can be expressed as, so this is going to dominate, all the VBC terms are small. So, you can say IS, I write P to ISP stands for the IS of the PNP transistor, all right, exponential VBE by VT for the PNP, okay. So, what is that voltage? V1, okay. Of course, it is VBE is minus V1, but see that the current directions all change, okay. So, I mean it is, we can write in terms of V1 by VT, all right. So, I naught is ISP exponential V1 by VT, okay. So, this I naught value is given by this, okay, all right. Now, so we have to see that this condition is satisfied, okay. Now, at this point the next thing what we do is we write an equation of the current at this point, okay. So, when this transistor goes to saturation, it means that all the transistors okay, all the transistors whose collectors are connected at this point are cut off. Okay. So, whatever current collector current is flowing for this PNP, that is P1, flows in as base current of the NPN transistor. Okay. All right. So, we can write an expression. So, at say I will call this node A, I will call this node A, say, okay. Collector current IC of PNP is equal to IB of NPN. Okay. So, what is the collector current of PNP given by? Again we go to the Ebers-Moll equation. Okay. So, ISP, collector current is this current source minus this current source, all right. So, I write ISP exponential VBE, VBE of the PNP is again V1, all right, V1 by VT minus exponential VBC by VT, which is V exponential V2 by VT, okay, minus this current source, all right. So, ISP by beta P, that is the beta of the PNP transistor. Actually this should be the reverse beta of the PNP transistor, but since the PNP transistor is a lateral transistor, okay, all right, it is not a vertical transistor, it is a lateral transistor with the two emitters and collectors, okay, side by side. The reverse and the forward betas are almost the same, okay. So, we can take it as beta P, okay, which is the beta of the PNP transistor, okay, all right. So, ISP beta P exponential the base collector voltage. Base collector voltage of the PNP is again V1, okay. So, this is the collector current of the PNP transistor, okay, and this has to be equated to the base current of the NPN transistor. So, what is the base current of the NPN transistor? So, this is, I shall write it, this is ICPNP, okay. IB NPN is going to be equal to, again the sum of the base current is the sum of these two current sources, okay, for the NPN. So, we have already taken that. So, ISN, so there N times total base current ISN by beta N exponential V2 by VT. Okay. Okay. So, all right. So, what do you get now? So, we have to equate these two equations, all right, the ICPNP with IBNPN, all right, and then we have to get the condition for saturation. Okay. Now, once we equate that, you can write it this way. I will write the equation. Now, what you get finally, you can write it as ISP exponential V2 by VT is equal to, so this term take it on one side. So, you will have is equal to ISP exponential V1 by VT minus So, this is equal to this thing. Okay. So, this is going to be equal to plus the correct signs are just beta n exponential I think there is some mistake somewhere. At node A, ISP exponential V1 Vt minus exponential V2 by Vt minus BBC. Oh, this one is a mistake, I think. We have to be, this has to be minus exponential. This is for the PNP, this is base collector. Okay, base collector, this becomes, this is V2. I think we made a mistake here. All right, sorry. So, this is ISP by beta p, okay, for the PNP. Okay, just we go back here. All right, ISP exponential V1 by Vt, VBE by Vt minus VBC by Vt. Okay, so exponential V1 by Vt minus V2 by Vt. Okay, minus Is by beta r exponential VBC by Vt. So, for the PNP VBC is V2. So, this has to be V2, alright. So, this is going to be equated with this, alright. So, now I think I just rewrite this. This becomes ISP exponential V1 by Vt equals ISP exponential V2 by Vt plus ISP by beta p exponential V2 by Vt plus NISN exponential V2 by Vt. Okay, is it clear now? So, this is equal to, I can write ISP plus ISP by beta p plus NISN by beta n exponential V2 by Vt. All right. Now, ISP exponential V1 by Vt, what is that? That is the same as I naught, isn't it? ISP exponential V1 by Vt is given by I naught, we have already derived that. Okay. All right. So, this term which we have here, okay, is actually equal to I naught. So, I can write here this ISP exponential V1 by Vt is actually I naught, the left hand side is equal to I naught. So, I naught is equal to this expression. Okay. All right. Now, again coming back here, the condition for saturation is that ISN exponential V2 by Vt must be greater than I naught. All right. So, ISN exponential V2 by Vt must be greater than that, okay, which is again some term into exponential V2 by Vt. Okay. So, what can I write? ISN must be greater than. So, we see that we have removed all the voltage dependencies, which is very important. Okay. Okay. So, now we have a relation between the different saturation currents, the number of collectors and the beta of the transistors, okay, individual transistors. So, ISN must be greater than ISP plus ISP by beta p plus NISN by beta n. So, this condition must be satisfied, all right, in order to ensure that the transistor goes to saturation. Okay. Now, we will just do some small manipulation. You can write like this: ISN must be greater than ISP plus ISP by beta p must be greater than 1. Basically, this divided by this must be greater than 1. Okay? All right, or you can write 1 by 1 by ISP by ISN plus ISP by ISN into 1 by beta p plus n times n by beta n, okay, must be greater than 1. Okay. All right. So, this condition must be satisfied, okay, which means, so this is given by, so I will just make a box here, okay. So, this condition must be satisfied. So, when you say that this has to be greater than 1, okay, what does it tell you about the denominator? This denominator must be less than 1. Okay. Now, this denominator consists of 3 terms. Okay. So, if this a plus b plus c has to be less than 1, each individually has to be less than 1. Okay. All right. So, ISP must be less than ISN. So, the condition, some conditions we can write down straight away. I think I can remove all this now. Okay. ISP must be less than ISN. Okay. Then we can what can we say about beta p? So, this again this must be less than 1. Okay. So, ISP must be less than beta, you can write that ISP must be less than beta n times ISN, okay, sorry, beta p times, all right, which means that or we can write like this, ISP by ISN must be less than beta p. Okay. Also, n must be less than beta n. So, these conditions must be satisfied, okay. But one must be careful that these are necessary conditions, but they are not sufficient, okay. All right, in the sense that if this ensures that each of these individual terms in the denominator is less than 1, okay, but if each of these terms is less than 1, it does not mean that this is going to be greater than 1, okay. So, these are necessary conditions which must be satisfied, but these are not sufficient conditions, okay, all right. So, this must be as must make them as small as possible, okay, all right. Another term which is very often used, if you again go back to this, okay, is called the beta. So, these conditions must be satisfied. Another way of writing that expression is, one term is called the beta effective, all right, is equal to, right, beta n. So, if here you multiply both the numerator and denominator by beta n, okay, that expression there, you have beta n by n plus beta n by beta p ISP by ISN plus okay, this must be greater than 1 also. This is called the beta effective, okay, this term, all right. Okay, the same this here in this expression which we have shows that this fraction must be greater than 1, multiply the numerator and denominator by beta n on the left hand side. Okay, this also is greater than 1. So, this term, okay, you write like this. Okay, this is beta n divided by beta n is the actual beta of the NPN transistor, but this is the effective beta of the I squared L cell. Okay, that is, if you consider that in this PNP in this cell, which we go back to this cell, that is, if this current source is equal to this current source, okay, and then if you have an NPN transistor, okay, if the beta is greater than 1, the transistor should go to saturation. Okay, that is, if the collector current is the same as the base current, all right, okay, and then the condition for saturation is the beta must be greater than 1, isn't it? So, this is the effective beta. Okay, if you have the same, because you are having the from the same point you are having two PNP transistors here. Okay, so just because of this configuration here, you know, and because of the condition of these transistors, normally if both the transistors were identically biased, you know, these two transistors, you would have equal currents, all right, and then this transistor would go to saturation if the beta is greater than 1. Okay, all right. So, now what you have is an effective beta because of this, because of the different states of these two PNP transistors P1 and P2, all right. So, the effective beta must be greater than 1. Okay. So, the beta is modified as such if you consider it as a cell instead of as a transistor, okay, effective beta of the cell. So, beta n by n, okay, it is quite obvious that because you have n collectors, all right, you are having n times, the collector current is n times. Okay. Again, if you had same current sources I naught, the collector current would be n times I naught, okay, and this one would be I naught. Okay. Beta has to be greater than n for the transistor to go to saturation. So, this n is coming because of the large number of collectors, and the remaining terms in this, okay, this expression beta effective expression is coming because of the fact that the PNP transistors at the base is actually going to saturation, okay, which means that the current source at the collector and the base, they are different values, okay, they are not the same values. So, this is effectively modifying that expression. Okay. So, this is the beta effective of the I squared L cell, and this is a figure of merit, okay, for any I squared L cell, okay, and the larger this value, of course, it is better. Okay, and this must be greater than 1 for the transistor to go to saturation. This also tells us from this expression we can also calculate the different values of the different parameters, okay, that is required for the proper operation of the circuit. Okay. For example, I just give a small problem, say, okay, suppose you design such that ISP by ISN is equal to 0.2 and beta p is equal to 0.25, okay, and n is equal to 4, say, that is it has 4 collectors. So, what is the value of beta n necessary? All right, you can simply plug in the values in this expression, okay, and solve for beta n, okay, and it comes out that, of course, it is not a very large value, beta n must be greater than 6, okay, all right. So, this gives us a way of finding out the individual conditions for the transistor to operate properly, okay. This also tells us that one must do a proper design, okay, of the I squared L cell, okay, in order to ensure that the transistor is working. That is, if you just connect the transistors in that fashion, you know, it is not going to work, all right. For example, you see that if you look at this expression, okay, ISP must be less than ISN. Okay. Now, what is the expression for IS or the saturation current? IS in a transistor is given by, if you remember, AQ dN Ni squared by N, that is the base doping, I will write NB, okay, into WB. Okay. So, if you look at ISP must be less than ISN. Okay. So, what you have to do is you have to ensure that, well, dN ISP, so dP by, see, AQ Ni squared, they are constants. Okay. dP by NB WB of the PNP must be less than dN times NB WB of the NPN. Okay. Now, dP and dN, of course, dP is less than dN. Okay, that is the diffusion coefficient is of holes is less than that of electrons because of the mobility difference, you know that. But here you must be, so basically what you have to do is you have to ensure that this denominator, which is well, this is the base concentration and in the base width. Okay. So, this actually means the total base dopants per centimeter squared, okay, which is sometimes called by the Gummel number of the base also. Okay. So, this has to be for the NPN transistor. So, if this has to be less than that, this expression on the left hand side has to be less than that on the right hand side. So, this number for the NPN must be less. Okay, NBWP for NPN must be less than that of NBWP for PNP. Okay, all right, isn't it? So that this term on the right hand side is much greater than the term on the left hand side. Okay. Now, if you look back at the I squared L cell configuration, I will just draw it again. So, you have these are the different collectors. This is the N on N plus wafer. Okay. So, this is P, P, N plus, N plus. Okay. And so, this is the injector, this is the base contact, and these are the collector contacts. All right. So, the base for the NPN is this region, okay, and the base for the PNP is this region, base concentration. So, the base concentration of the PNP, all right, is this N, the substrate concentration, okay, and the base concentration for the NPN, because you are diffusing, okay, into the substrate, the base concentration of the NPN obviously is going to be higher than that of the PNP. Okay, NB for the NPN obviously is going to be higher than the PNP, because you are diffusing, you are creating that base of the NPN by diffusing into that substrate. Okay. So, again if you look back into this condition, okay, for the NPN, okay, the doping concentration is higher, okay, which means that this term becomes smaller, okay, which is going to create problems. Okay. So, what you have to do is WB of the NPN must be made much smaller than the WB of the PNP, that is the base width of the NPN must be made much smaller than the base width of the PNP. So, that this term, okay, NBWB, that product term is much less. Okay. All right. But at the same time you cannot make the base width of the PNP very large, because again you have a condition here, you see, all right. If you make the base width of the PNP very large, the beta of the transistor is going to fall. Again you have a condition that this ISP by ISN must be less than beta p. Okay. So, again beta p must be also sufficiently large. So, you see that there are a lot of interdependencies, okay, for the different conditions which must be satisfied, okay, in order to ensure that the I squared L cell works. Okay. So, just wanted to give you an idea that one has to really design the cell properly, okay, in order to ensure that this cell is going to work. Okay. All right. Okay. So, all right. So, this is so we just had an idea that one must properly design the cell in order to get proper operation of the I squared L cell. Okay. So, we shall go ahead with our discussion now again, and the next topic which we shall look at is the different characteristics of the I squared L cell as such, that is the noise margin and propagation delays, okay, by which you characterize a particular logic family. Okay. All right. Now, firstly, if we take up the noise margin, okay, that is quite obvious also that the noise margin in a I squared L cell is not going to be too good, okay, because of the fact that the voltage levels are constrained to within 0.2 to 0.7 volts at each node. Okay. All right, because 0.2 volts when the transistor goes to saturation at a node, and this voltage cannot exceed about 0.7 or slightly more maybe, because of the fact that this is the base voltage of this transistor and it cannot exceed a certain value. Okay. So, the voltage swings, okay, is going to be much lower. But in the I squared L case, you see that the circuit is very peculiar in the sense that it contains there are no resistances in the circuit, all right, and so there are no voltage drops across the resistance. It is just the current which is flowing, okay, and which is switched either into the base or into the collector of the previous transistor. So, usually the noise margins here are defined in a different way, that is, instead of defining them in terms of the voltages, okay, here it is defined in terms of current, all right, okay, that is how much current noise, okay, it can withstand. Okay. And well, it is very difficult to get exact figures, but some simplistic analysis has been done, and it just gives you an idea of how to the whole idea is how to increase the noise margin. All right. So, let us take a very simplistic case again, although we know it is not correct, that we assume current sources, all right, say this n collectors and each of them current sources, and let us assume that these all current sources have the same value. Okay. All right. Okay. Just although as we just done in our analysis, we know that these values are not going to be the same, okay, but just to have some idea. All right. Now, suppose this transistor is off, okay, which means that suppose in this base node you have transistors connected here, okay, which again have current sources at their base, all right, and there may be m such transistors. Okay, so this is there are n collectors, and here let there be m transistors. Okay, m transistors, all right, at the base. Okay. Now, when any of these transistors go to saturation, this current source is going to go this way. Okay, the current flows into the collector and this transistor turns off. Okay. All right. Okay. Now, suppose you have another current source here, which is due to noise. Okay, I'll call this IN, say, noise current. All right, and this current flows in here. What is going to happen is if this current is less small, okay, again this current, most of the current will be flowing into the base, into the collectors of the previous transistors. But if this collector current, if this current becomes sufficiently large at this node, okay, then this base may get in, sufficient current to turn it on from the off state. Okay. So, what is this value of this current, okay, which turns this transistor on, okay, that is defined as the noise margin in this case, all right. So, this is a current source, okay, and this transistor is off, okay. So, what is this value of current, noise current, okay, which turns this transistor on, okay, that is defined as the noise margin in this case, okay. So, if this is very large, that means it can sustain a very large noise current and still remain off, okay, all right. So, how do you calculate this value? Okay. So, if you have n collectors like this, okay, so the total collector current is n I naught, okay, collector current is n I naught, okay. So, we shall consider that this transistor, okay, to be turning on, okay, when base current, okay, at I should say base current, we have to assume certain base current, okay, when you say that this transistor is reasonably turned on. So, base current at turn on, okay, it says n I naught by beta, okay, of course this is beta n of the NPN transistor, okay, all right. Okay. Now, at this node, if you now write the nodal equation, okay, so what you have is currents flowing in, okay, what you have is I n plus I naught, the currents flowing in, okay, equals n I naught by beta, okay, plus here, okay, you can have a condition, okay, when you can have one transistor on, you can have two transistors on, or you can have all m transistors on, okay. So, let us say that, well, m is the number of transistors which is on, okay, I mean m prime or something, okay. So, all right. Now, what is going to happen is m prime, so if m transistors are on, okay, so this can draw a current of beta times I naught, each of them at the base you have a current of I naught, all right. So, these can draw a current of beta times I naught, okay. So, m prime beta n I naught, okay. So, I naught is equal to, sorry, I n, that is the noise current, okay. I n, actually this is called I n O, that is 0, okay, when, because this transistor is off condition, is equal to I naught, okay, n by beta plus m beta minus 1. Okay. The interesting point here is, well, this we have done this analysis, there are a lot of assumptions involved, okay, and we have taken equal currents, but the important point here is, which comes out from here, is that this is proportional to I naught, okay, all right. The noise current is proportional to I naught, okay. That is, if you want to increase the noise margin, you have to increase I naught, okay. So, the circuit becomes more immune to noise if you increase I naught, all right, all right. To improve the noise margin, one has to have higher injector current. Okay. So, that is the message from this expression. Okay. Similarly, one can do an analysis when this transistor is on. Okay. When this transistor is on, this current is flowing into the base. Okay. To turn it off, okay, when you turn it on, it is simpler because it means that all these transistors connected at the base should be off. All right. So, again if we do the case for the transistor being on, okay, what you have to do is the current source, the noise current source, okay, it has to be the other direction. Okay. It is basically drawing the current. Okay. And again, so this has to be turned off. Okay. So, what is the condition? Again here the condition is the base current, again we will assume that this transistor, okay, goes out of saturation when, all right, you have this condition when the base current, all right, falls to n I naught by beta n. Okay. All right. So, you have again if you write the nodal equation at that point. So, all these transistors are off. So, they do not contribute to any current. Okay. So, the current flowing in I naught is equal to I n plus n I naught by beta n. Okay. So, we have I n equals to I naught one minus okay. All right. So, again it is proportional to I naught, okay, and the current the noise margin is going to be larger when of course beta n is large, okay, compared to n, okay, and of course this also implies that beta n must be greater than n, all right, in order to for this to be positive quantity, all right, which is also a condition which we got from the previous analysis which we did, the condition for proper operation of the I squared L cell, beta n must be greater than n. Okay. So, again the noise margin is proportional to I is proportional to I naught. Okay. So, to improve noise margin we must increase the injector current, okay, for the I squared L cell, that is the current which is flowing in. If you go back to the figure of the I squared L cell, okay, the current which is flowing in here, okay, has to be made, if you want to increase noise margin you have to make it as large as possible, but of course that is going to add to the power dissipation, all right. So, again there is a trade off between noise margin and power dissipation, okay. So, if you increase the current here flowing into the cell, that is if you reduce R, because this voltage is around 0.7 to 0.8 volts. So, if you reduce R you have larger current, which would mean that there is going to be a proportional increase of current flowing into the individual through the individual injectors, okay, all right. So, that is going to improve the noise margin. Okay. So, we will stop here today. The next class we shall take up the propagation delay problem and with I squared L cell. That is in fact one of the major problems which I squared L ran into after having such a impressive start, we should say, because people thought initially that it is very good circuit, okay, but it ran into problems because of the propagation delay. We will discuss that in the next class.